Good morning to you all. It's a great pleasure and honor for me to be here to speak to you. And I'm particularly going to talk to you about things which are relevant to the Korean failures we've heard recently, and particularly to the 2012 failures of the British helicopters that went down in the North Sea and others. All these have been metallurgical problems. They've all failed by fatigue. And today I want to talk to you about those cracks and how we can prevent them such that you would never, ever suffer a fatigue failure in any rotorcraft ever again. And I think this is easily possible, and we can do it starting tomorrow. And so we have a look at our conventional thinking. If we look through a microscope and we see an inclusion with a crack, the standard thinking is that the inclusion was there first, that we applied a stress, and finally the inclusion cracked and set off a crack in our metal, and we had a failure. Now that's the standard thinking, and is quite logical and seems straightforward. Unfortunately, it's completely wrong. The real explanation is that the crack was there first. The inclusion forms on the crack, and no stress is involved at all. Our metals are pre-cracked. They're cracked from the day we pick them off a shelf and start to machine them and make them into a component. They're already cracked when they go into service. And it's very, very important we realize this. So if we proceed, these cracks start from the casting process. When the metallurgist first makes his metal, and he makes it by melting it and casting it. Now, if he can fill his mold by filling it uphill, there's no problem. What happens is, as you look into the mold as the metal's coming up, you can see an oxide on the surface. And the oxide moves in a very special way. It splits and moves to one side, but immediately reforms, splits again and reforms, splits and reforms. And so you see that surface oxide becomes the skin of the casting. And there's no problem. That metal is free of defects. But we almost never make castings like that. We make them like this. We pour them, and now something terrible happens. We're folding in that oxide. Now, let me just talk about this because it's extremely important you realize what's happening. Here's our oxide. Here is air or a vacuum. It doesn't make any difference. The vacuum is only dilute air. So air or vacuum, I'm here. Here's the metal. Here is our oxide. So the underside is in atomic, perfect contact with the liquid metal. But the top is like sandpaper, or completely dry. Now, if we, in this case, we're pouring turbulently, and if this happens, now this dry surface meets this dry surface, so there's no bonding between these two surfaces. And now this goes off into our liquid as a crack inside the liquid. And so by pouring turbulently, which is how most of our steels are made, we are filling our liquid steel with cracks. These are what I call bifilms. This is our single film on the surface of the metal. When it goes inside the metal, it goes in as a double film, which I call a bifilm. And the bifilm is a crack. So every oxide we find in our metals is always double, it's always a crack. And our metals, all our steels, are filled to different degrees with cracks, depending on how turbulently they're cast. And this is the situation. You see here biofilms being made, and this is the kind of thing we see. This happens to be liquid aluminum. So these are what I call entrainment defects. They're biofilms, and every now and again we have this other special defect which goes in, which is a packet of air, which has this special scientific name called an air bubble. Okay. And this again is some liquid aluminium, which we look at by X-ray. So this is a radiograph of a piece of aluminium which has been cast. You can see it is full, it's literally full of cracks. So when we talk about our housings and precision cast housings, I worry that it's maybe full of cracks, depending on how turbulently it's been cast. Now, it need not be cast turbulently. There does not need to be cracks present in the metal. But if it's poured turbulently, there will be cracks, and the possibility is the casting will fail. I mean, I can't emphasize how serious these things are, but you are the customers. It's up to you to specify how your castings are made, and you must insist that they're free from cracks. The foundry will always tell you their castings are perfect, but you have to make sure, and it's for certain, it will not be true. Okay? So here we are. This is the way steels are poured. It's absolutely terrible. The thing is poured through a height of at least 2 or 3, 4, maybe 5 meters, and it's all churned in such that it churns in the maximum number of defects to make sure the steel is as unreliable as possible. Okay? And this is the way an ingot is usually top poured, which is terrible. And then people say, oh, well, we don't top pour, we uphill team. This is the bottom gating system, which is much, much better. This is not true. This is just about as bad. Both of these are seriously bad steels. There is a new technique which I'm trying to promote. I call it contact pouring. We haven't time to talk about this too much today. Maybe we'll get some time later during the conference. But contact pouring makes a fantastic difference to the quality of steel. If you're using just normally cast material in this way. But for instance, if you're going on to use a secondary refined material, a secondary remelted material, like vacuum arc refining or like electroslag refining, these are interesting processes. I'm going to be talking about these in a minute. But you need an electrode for those processes, which you have to melt down and then form an ingot. And if you wanted a really good electrode, you would do it by contact pouring. Most of our electrodes are made by top pouring. Now, people say, oh, it's no problem. We top pour in vacuum. This is vacuum induction melting, VIM. And VIM is perfect. I'm very sorry to tell you, it is terrible. I would never use it. Never, ever use it. Okay? Contact pouring in air would give you an infinitely better electrode. And then you have a chance, when it's remelted, to get a really high-quality product for the first time. Just let's look at a few products which are suffering right now, not in your industry. This is a surface of a main bearing of a wind turbine. And as you probably know, wind turbines are designed and built for a 20-year life, and then you get a good economic performance. However, many wind turbines are failing by fatigue of the main bearing after only 5 years. And this is going to wreck the whole economics of wind power. And so a standard metallurgist would look at this and say, fatigue failure. These are bifilms. These are bifilms which are cracks in the main bearing because the bearing was poured badly. When it was cast, it was poured turbulently. We folded in the surface oxide, and these cracks you see are the folded in surface oxide. They are bifilm cracks. And of course the main bearing fails by fatigue. It's designed to fail by fatigue because it's already full of cracks, just because it was poured badly. And it need not have been poured badly. It's easy to pour well. And here's a machine surface of a nickel-based alloy, and you can see the cutting tool was rather blunt, and so it's torn open the bifilms, and you can see hundreds and thousands of bifilms in this nickel alloy. Again, they need not be there. It's easy to cast nickel alloys without bifilms. Here's again another nickel alloy. You can see the cracks. You can see the turned edge again. And here's a wonderful example of a tensile test piece full of cracks. Every one of them is a bifilm put in from the casting process. And again, it's not necessary to do this. This nickel alloy is beautifully ductile and will stretch and stretch like a piece of plasticine. It would never crack. And now, remember this. Here we have cracks because of bifilms. You take bifilms away, which is easy to do, and now your metal never cracks. There is no crack mechanism built into metals. I'm talking most of our engineering metals now, like steels, like nickel base, copper base, aluminium. All of these materials are ductile and would never, never crack. If they crack, you know it's a bifilm problem, and you know it was put in from the casting process before you ever received the steel or the alloy. And just a little bit of metallurgy while we have time. These are images of bifilm cracks. And during the solidification process, inclusions have formed, and they always form on the cracks. And so what you can see here are long cracks in this particular alloy, in which a beta ion, which is people call it a brittle precipitate, but actually it's not at all brittle, it is ductile. It looks brittle because it contains bifilm cracks, so certainly it looks brittle. And then there's silicon metal as well here in this same image that also was formed on a bifilm. And so all these secondary precipitates seem to always form on bifilms. And so the inclusions we find, like carbides in steels, which are cracked and sitting at grain boundaries, if they're cracked, it tells you that they've formed on bifilms, and there's a bifilm sitting there at the grain boundary. So we have to rethink our metallurgy. And here again, this is a ductile failure, but there are particles in there, inclusions, which appear to be brittle. But they only appear to be brittle because they've nucleated and grown on bifilms. And so what happens if we have a bifilm, as we see here, if we have a machine surface that cuts into the bifilm, and if the bifilm has inclusions and second phases precipitated on it, and now we introduce some corrodant, maybe rainwater, maybe seawater. And this is a way now of the corrodant getting deep inside the metal. And as it goes in, of course, it makes secondary corrosion couples with the existing inclusions. And so now it goes twice as fast as it would normally go and becomes an extremely serious and very deep crack very quickly. And so what happens is that the surface now will develop into an etch pit. This is just a tiny depression in the surface. Here is an etch pit. And these are the cracks. And a metallurgist would say, oh, the cracks are fatigue cracks, which have been formed from the etch pit. It's not possible to grow fatigue cracks from etch pits. Etch pits are incredibly tiny. They're about the size of the head of a pin. So there's almost zero stress concentration because of an etch pit. Therefore, a fatigue crack would never, ever grow from an etch pit. These are bifilm cracks, and they were there first, and they caused the etch pit. So when you have an etch pit, and what appears to be a fatigue crack from the etch pit, the reality is the fatigue crack was actually a bifilm, and the etch pit forms just at the entrance. So the position, the appearance of an etch pit tells you that there's a bifilm at that point, and the bifilm can be very, very long and very deep and be a huge crack into your component. And this brings me on to vacuum arc refining. Here is a process whereby we take an electrode, we put a powerful currents, electrical currents through the electrode, make a powerful spark, melt off the tip of the electrode to make an ingot. And all this happens in a vacuum. I should say, a so-called vacuum. Don't forget that all vacuums are like dilute air. And so, as we melt, the surface of the ingot becomes oxidized because there's plenty of oxygen still in the vacuum. And now we have our dry surface of oxide, but now more droplets form and more metal flows around, and as it flows, the new surface is also covered in oxide. And as the new surface rolls over the old, we're rolling over a new oxide film onto the old one. And we're getting a double oxide film, a bifilm crack. And so it's very, very unfortunate that this process, which all of us in this room are using today, is formed by a process of making cracks up the length of the ingot. And here is a cross-section. You might say, how do you know this is true? That's easy to answer, because if you take a vacuum arc refined ingot and you put it into a forge and you try to forge it, it immediately cracks. So you know that the surface is already pre-cracked and easily opens. And that's with the most ductile of materials. And if instead of vacuum arc, you went to electroslag melting, and you took your same electrode and went through a slag, drop by drop, to make an electroslag ingot, that ingot has perfect surfaces because they're all formed inside a liquid. You can't make cracks in that process. And there you take that ingot, you put it into a forge, you forge it, it forges like butter. It forges beautifully because there are 0 cracks in it. With the vacuum arc ingot, as you see on the screen now, you have to machine away the surface. You machine away the surface cracks. But you never know. You never know whether you've machined away every crack. And here they are. They're still there. You could never machine away every crack. And so this vacuum arc material, which all of you are building all your rotorcraft from now, and all the key drive shaft components and the key gears in the key gearboxes, all the drive components all the way through, you're using vacuum arc remelted steel, for God's sake. You have to stop using this material. You have to say to your supplier, we're going to change to electroslag material. You see, the rotor shafts for the helicopters which ditched in the North Sea in 2012, they all had so-called fatigue cracks from etch pits, which no one in the world could explain. And of course they couldn't explain because they thought they were fatigue cracks, which they were not. They were bifilm cracks in vacuum arc remelted steels. And those rotor shafts, or the other components, are all designed with about a safety factor of 5 and still failed by fatigue. Now, had they been made without bifilms, you would have only needed a safety factor of 1, and it would have been safer because the thing would never have cracked. Because steels and other of our engineering metals don't crack. It's not possible to make them crack unless you have bifilms there, and which are only put there if you cast and melt badly. And you need not do that, and you need not buy you need not buy vacuum arc remelted material. You could move on to electroslag. There's much more to say about this, and even the electroslag could be made to be better. But today we don't have time for that. But what we do have time for is for you to say to your suppliers of steels from which you make all your key parts, we don't want vacuum arc remelted steel. We do want electroslag. And what's more, for the future, we want improved electroslag. And that's something for another day. Thank you.